comet is on an extremely unusual path, moving too fast to be bound by the sun's gravity, breaking a typically seen orbital trajectory.
A silent visitor from deep space is breaking the rules. We thought applied to comets. It vents a metal gas rarely seen outside human industry, and its jet points toward the sun instead of away from it. This object, 3I Atlas, has chemistry. So unusual, scientists are rethinking how interstellar bodies form and evolve. A stranger appears. In July 2025, astronomers found 3I Atlas on a hyperbolic path, proof it came from beyond the sun's reach. It looked big and active. Observatories worldwide, Hubble, the James Webb Space Telescope, and Keck tracked it. By August, Keck spectroscopy delivered the shock. Atlas was venting nickel at about 4 grams per second with no detectable iron. In ordinary comets, nickel and iron appear together. Seeing nickel alone is like hearing a duet, sung by one voice. The missing partner demands an explanation. The lines revealed nickel, tetracarbonyl NiCO4, a reactive compound best known on Earth from controlled metallurgical processes. In nature, it is extremely rare because it needs abundant carbon monoxide, suitable temperatures, and a ready nickel source. Yet Atlas showed clear signatures of it. Images added another twist. Instead of the classic tail swept away from the sun, Atlas showed a narrow jet pointing toward it. The jet was mostly carbon dioxide and water vapor, with faint cyanide and nickel compounds, but still no iron. The ratios were extreme. CO2 to H2O hovered around 8:1, among the highest ever measured for a comet-like body. Atlas also looked odd in polarized light. Its dust produced unusually strong negative polarization, hinting at compact, fine-grained, or highly processed surfaces, unlike typical comet dust. Expected high-resolution images from the Mars Reconnaissance Orbiter's high-rise camera were delayed by a U.S. government shutdown, so teams are modeling the physics from the data in hand. A chemical puzzle. NiCO4 should be difficult to make and keep in the gas phase at comet-like distances. Its presence suggests Atlas either contains nickel reservoirs that meet abundant carbon monoxide at the right temperatures, or sunlight and space weather create the molecule on the surface and loft it into space. A leading idea casts Atlas as a natural body, born in a carbon-rich region far from its original star. In such a disk, iron and nickel could segregate, nickel-bearing phases near the surface, iron deeper, or locked-in minerals that do not sublimate. Over millions of years in interstellar space, radiation may have altered the outer layers, freeing nickel while leaving iron, trapped or transformed into non-volatile forms. When warmed by sunlight in the presence of CO and CO2, those layers could produce NiCO4 and release it as vapor. The high CO2 to H2O ratio supports a carbon-dominated birthplace. The missing iron lines may simply reflect storage. Iron is present, but not in a state or location that vents under current heating. Polarimetry points to compact crusts that trap volatiles until vents open, releasing focused streams. If those vents sit on sunlit slopes with steep thermal gradients, outflow can be channeled in counterintuitive directions. Combined with the inertia of heavier grains and the thrust of CO2 through narrow conduits, this could steer material sunward. Despite radiation pressure, another factor could be dust properties. Ultrafine, electrically charged grains, possibly coated by films, from nickel chemistry might respond differently to sunlight. Under some conditions, gas flow near the nucleus dominates, guiding particles along pressure gradients that aim toward the sun. Laboratories are testing these ideas by heating analog ices, water, carbon monoxide, and carbon dioxide, plus trace metals under comet-like conditions to see whether nickel-4 forms efficiently and whether iron emissions are naturally weak. If it does, a natural origin gains traction. If not, the models must change. Debate impossibilities. Most researchers favor exotic but natural explanations, yet the anomalies have prompted some to consider bolder ideas. Harvard's Avi Loeb has suggested parts of Atlas's behavior could be technological rather than geological. The nickel compound as a byproduct of engineered coatings, a jet driven by non-cometary processes and features that might qualify as a technosignature. The broader community is cautious. Extraordinary claims need extraordinary evidence, and the current data do not meet that bar. Nickel-cobalt-4 can arise through known pathways. Jet direction can be set by local topography, vent geometry, and gas dynamics. Atlas's trajectory is consistent with an unbound interstellar object. Until observations reveal uniquely technological structure, regular modulation, engineered reflectivity patterns, or components not produced by natural processes, prudence will prevail. Even so, techno-signature thinking is useful because it forces stronger tests. If cometary heating can produce metal emissions that mimic industrial signals, future searches must account for that natural background. Conversely, if certain spectral or dynamical features resist every natural pathway, they become stronger candidates for targeted follow-up. Atlas also fits a broader pattern. Interstellar objects are diverse. Oumuamua showed non-gravitational acceleration without a visible tail, likely due to undetected outgassing. 2I/Borisov looked like a textbook comet. Atlas adds a third archetype: massive, CO2-dominated, metal-emitting, optically peculiar, with a jet that ignores standard tail geometry. The implications touch planet formation. If Atlas truly vents nickel without iron, it challenges assumptions about how metals partition in young disks and how planetary cores and crusts evolve. Optical behavior matters too. Extreme negative polarization points to welded crusts that polarimetry can flag quickly, and a sun-facing jet means torque. Torque changes spin, orientation, and can fracture the surface. What comes next? The immediate need is more data. Delayed HIRAS images should show whether the jet comes from a single vent or a line of fractures. If one vent dominates, shape and orientation could explain the inverted direction. If multiple vents feed a sheet of gas, crust layering and fracture mechanics move to center stage. Spectroscopy from Keck, JWST, and others will keep tracking nickel. If NiCO rises and falls with solar heating that supports natural chemistry, if the nickel signal varies independently or tracks rotation or vent geometry, then gas dynamics and crust failure may control the release. Teams will also push harder on iron searches. Even a faint, phase-matched line would refine models of how both metals are stored and freed. Polarimetric campaigns will map polarization versus phase angle to infer grain size, porosity, and compactness of the surface and lofted dust. If Atlas's negative polarization stays extreme across angles, it will mark unusual dust physics. The Vera C. Rubin Observatory will reshape the field by finding many more interstellar interlopers, earlier and fainter. With more lead time, astronomers can coordinate spectroscopy, polarimetry, and thermal imaging ahead of peak activity. A larger sample will show whether a Co2-heavy, nickel-rich body is rare or part of a hidden population. Meanwhile, labs will probe whether solar-like radiation can assemble NiCO4 in layered ices, how fast it breaks under ultraviolet light, and how easily it escapes through microfractures. If rates match the observed nickel release, alongside the lack of iron lines, we will have a cohesive, natural explanation. If the anomaly persists, robust nickel with no iron, a sun-facing jet without a convincing model, and spectra that resist every natural pathway, then more speculative ideas will gain weight. That does not automatically mean technology. It could point to rare mineral phases, extreme redox environments, or fragments shaped in the atmospheres of evaporating subneptunes. Whatever the outcome, Atlas is already a landmark. It expands the chemical and physical space for interstellar bodies, shows the power of rapid, multi-wavelength follow-up, and reminds us our comet playbook has limits. It also offers a practical lesson. When a new interstellar object appears, mobilize spectroscopy to read chemistry, polarimetry to map textures, high-resolution imaging to chart vents and fractures, and time series observation to track spin and outgassing. As Atlas continues its passage, we will see whether the nickel signal strengthens or fades, whether the jet keeps its sunward aim or splits into new directions, and whether images reveal the surface structures capable of such behavior. If nickel without iron survives scrutiny, astrochemistry must adapt. If the results find a natural niche, our catalog of possibilities still grows. Either way, Atlas has already changed what we expect from interstellar visitors. Thanks for watching. Don't forget to subscribe to Epic Dive for more amazing documentaries.